Hey everybody, this is Mr. Munson, Unit 2, Circles. And we're continuing with Concept 3. We're going to look at some special cases. We've been dealing with vertices on the inside and then on the circle, looking at the arcs and angle relationships. Today we're going to look at the arc and angle relationship, but we're going to continue with the vertex on the inside, but not at the center like a central angle is. And then we're going to look at a case where the vertex is on the circle, but one of the sides is a tangent. So if you look at these two shapes down below, these is kind of like what we're going to be dealing with. Let's get started. So far we've been looking at these two cases. In the part one video, we did central angle, and we found that the angle whose vertex is on the center of the circle is equal to the arc that it cuts. Then we have the inscribed angle, and we find that the angle there, when the vertex is on the circle, is equal to half the arc it cuts. Now I'm going to kind of rewrite that equation there and start writing it differently from this point on. All right, so that's exactly the same thing. I take half the arc, okay? Now you'll see as we move through a couple other special cases why I'm going to divide by 2 versus just multiplying by half. I end up with the same result, but this will make remembering the equation easier since it's basically a fraction on that side versus a fraction times something else, okay? We're about trying to make it so that our minds can wrap our heads around these ideas in the most simplistic ways. The cool thing is that once we have this kind of equation, instead of multiplying through, we just see that it's a fraction, and so then we can cross multiply and solve when it's a little bit more difficult. All right, let's continue. So we have a central angle here, and what we find is that a central angle is an angle that cuts one arc. Okay? As we begin this next lesson, what we find is the angle that we're going to form that's off-center is going to actually create 2 arcs. It's going to cut 2 arcs. And so we're going to have to kind of think through a relationship that's not so pleasant. It's not so straightforward as just angle equals an arc. You'll see why. All right, so here we have a circle. That red dot is a center of the circle. So what's happened is we have 2 chords that meet off center. So this is not a central angle. And so what ends up happening is if you look at angles 1 and 2, those 2 angles are vertical angles. We know that those 2 angles are exactly the same measure. Now the blue 2 cuts an arc that comes up here. And the green arc or angle cuts this arc down here. Now, as I was just saying, in a central angle, we have one angle and it cuts an arc and it's the same. But here we have 2 angles, angles 1 and 2, but they cut 2 completely different arcs. And what we find is that those arc lengths or arc measures will be different as well. So there's not a 1-to-1 correlation. There's actually 2 angles cut in 2 arcs. It can get kind of confusing. So what I want to do is, let's say I look at angle 1. What I find is that the measure of angle 1 is equal to adding up the 2 other arcs, or adding up the 2 arcs and divide by 2. Basically taking the average. We're going to average the 2 arcs, and that will equal the measure of angle 1. The exact same relationship is going to be the same for angle 2. And the reason is because angle 1 and angle 2 are in the same measure. So if I wanted to find angle 2, again, I would just simply average the 2 arcs that are cut by these 2 similar angles. Now I'm going to come up with a set of words that I think are helpful to remember this relationship. So the relationship over here on the right hand side is that the measure of the angle is equal to the big plus the, what do you think? I hope that you can come up with the word small, right? And so if we take the big arc and the small arc, add them together, divide by 2, we get the average of these 2 arcs. And that, in fact, is equal to the angle. All right, so I'm going to move that idea down to be a little bit smaller and just out of the way. Hopefully that was there big enough for you to have in your notes. And let's look at an example. Now let's just analyze this a little bit. We see the angle X is right here, and there's two arcs that are associated with it. This one here that's directly across from it, and of course the one that the vertical one cuts. So here's our second one. So now this is what we know. It's a vertex off center, and that the relationship is the measure of the angle is equal to the big arc plus the small arc divided by 2. And in this particular drawing, it's quite easy to see that the big arc is 170 and the small arc is 70. What I want you to know is that I don't want you to worry too much about deciding which one's big and which one's small. The reason is because, well, if I take a 5 and add it to a 10 and a 10 to a 5, I get the same number. Adding two numbers together, it really doesn't matter which one's big and which one's small. Hopefully that'll pay out a little bit more as we kind of go through some examples and talk about it. All right, so I'm going to slide that up, and let's go ahead and start putting in some information. So the measure of the angle is x, of course, and the big arc is 170 plus the small arc, 70, divided by 2. So we find out that the measure of the angle is 120 degrees. So the angle has a relationship with the arcs, but because there's two arcs there, it's going to take the average of the two. Let's do another one. All right, using the one I just did as a model, you go ahead and set up the equation, and you could come up with your own variable for that angle. You can write the measure of angle EBD right into the equation that you're going to use. But in any case, go ahead and set something up, an equation. Go ahead and set up an equation, and then go ahead and solve for the angle EBD. Put me on pause and go to work. All right, I got it to equal 79 degrees. If you didn't, look over my work, see if it's any different than what you did, and let's go ahead and continue on. All right, now this next one is an example, so I want you to walk along with me, but what I want you to do is first put me on pause and see if you can write the equation for this one, and then you can come back and just check your work. Don't worry about solving it. I want to walk with you as we solve it. So put me on pause and see if you can write the equation. All right, and there I have it. I have the sum of the two angles divided by 2 equals 53 degrees. Now again, is the 3x plus 3 the bigger one or the 10x minus 4? It really doesn't matter when we're adding two arcs. Later on, we're going to have a scenario where we're subtracting. It's going to be really important that you keep track of which one's big and which one's small in that scenario. Okay, so let's go ahead and walk through and solve this equation together. Okay, so I just simplified. On the top there of that equation, I just put together my common terms. Let's see if you can figure out what I just did there. All I did is I saw the left side as as a fraction, 53 over 1. Cross multiplied. 53 times 2 is 106. 1 times that 13x minus 11 is 13x minus 11. Now I'm just going to simply use my algebra skills at this point to solve. You go ahead and do that part on your own. Come back and check. So I got x equals 9. That's how we do it. Let's look at another one. All right, so let's take a look at this problem. Let's write some equations. Why don't you put me on pause and write the equation to find x, and then we'll work on one for y. So I think in a problem like this where there's x and y's and different things happening, sometimes it's helpful to use some colors to help us identify which pieces go with which angles. So x and its vertical are marked in blue, and then I'm highlighting the arcs so I know which ones go with x. Cool. Now I'm assuming that you could do that on a calculator and you're off and running. Now let's look at y. Y is going to require some thought here. So here's y and its vertical. And so we know that y is, again, the scenario where the angle is equal to the big arc plus the small arc. So I can fill in the stuff that I know. Let's see, y is the angle, and 70 is one of the arcs. I'm not sure if it's the big one or small one. The arc is missing that I need. And so I need to think about it. Let's see, here's the 70. It's this one out here that I need. So see if you can put me on pause and contemplate, how would I actually find out what that number is? There's enough information there for you to figure out what the actual physical measurement is of that arc. Okay, put me on pause and see if you can do that. So were you able to figure it out? I got 148. 148 degrees. And the reason is because it's basically 360 minus everything else. And that leaves me 148 degrees. All right, so that's enough. We've done equations like that. We know to cross multiply and solve it. Let's continue on. All right, so continue on. We're looking now at vertex on the circle. This is actually something we've covered before. So we're just going to look at what's going to appear to the untrained eye is something completely different, but it's really still the same. The reason this is a vertex on the circle is because, well, the vertex is on the circle. The relationship is the angle cut. The angle that we're talking about cuts an arc. And if I take the arc measure and divide it by 2, I get the angle. Or if I have the angle, I'll place it into the angle spot and solve for the missing arc, and so on. It's not hard at all. So let me show you kind of a variation of this. Now, to the untrained eye, this looks like a completely, absolutely different problem, but it's not. It's the same one. We have angles that are formed, and their vertices are on the circle. Okay? What's really cool is the relationship is exactly the same. We identify it as a vertex on the circle, and the measure of the angle is equal to half the arc. Okay, so let's look at an example. Okay, so here we are. We have this drawing, and it's basically a circle with a tangent and a secant. Okay, so here's the tangent, and here's the secant. Now, that tangent is what makes it look a little bit more confusing. But if I wanted to know what that angle is right there, let's call it, so it'd be called what, angle BAD. How clever. I would be looking at a vertex on the circle kind of condition. And I would immediately write down vertex on circle, write my relationship. The angle is equal to half the arc. And then I would just simply take that and start writing an equation. And it's that simple. Okay? You don't need to make it any harder than that. Now, suppose I was asking you, what is the measure of this arc over on this side? See if you can put me on pause and just think through. It's a really simple solution to that. So if you are having some difficulty with it, then I would encourage you to come right back and see how I'm going to do it. But the easiest way is to realize that the entire circle is made up of its arcs, and we have two arcs here. One is 124, and then the other arc is the one I'm looking for. So 360 minus 124 equals 236. Now, a little bit more complicated way of doing it, and unnecessary to do it this way, would be to do it like this. Well, we could look at the 62, which we found to be that angle right there, and we find that it's a linear pair with that other angle that's on the other side. So that angle right there is 118. Double it, and you get that 236. I don't particularly care for that method, but that problem-solving skill that I just showed you can come in handy for, a little bit more difficult problems later on in the process. All right, well, there you go. Put it on pause and come back and check to see if you did this one correctly. Remember, identify what kind of problem is, go ahead and write it down. Write down the, standard equation for it, and then set it up and come back and check your work. Right? Not too hard. So two types of problems that we're dealing with are very similar to what we've dealt with in the first half of 2.3. We have kind of this new idea where we have off-center vertices, and then this one where the vertex is still on the circle, but the angle kind of, drapes outside of the circle and kind of gives us an impression that maybe it's a different kind of problem, but it's not. It's completely the same because the vertex is on the circle. Same kind of equation and everything. All right, there you go. Draw your line, write a summary. Go back and look at it. For the best of students, I'm encouraging you to write as good of a summary as you need to so that you could solidify in your head the thoughts that we've had going through this video. Okay, let's move on to our try or do it problems. All right, so let's take a look at our do it problems. I'm going to scroll through these so you can see each one and write it into your problems. Remember, you should be putting these drawings in there if you're looking for full credit. I'm been started to deduct points for you not having the original work. I'm deducting points for it not being neat or I can't find stuff. So I encourage you to take your time, write these things down, do the problems as if you're trying to learn something, and have a good time. All right? Let's scroll through it. All right, that's it. See you next class.